Hello, and welcome to today's webinar with TE Connectivity. My name is Megan Frayne, and I am your moderator for our webinar. Over the next 45 minutes, the focus will be on sensors for electric vehicles and the critical role of sensors in the electric powertrain. Before I introduce our speakers, I want to start with some housekeeping items. At the end of today's presentation, we will have time for a Q&A session. I want to encourage everyone joining us to ask questions in the chat panel. We'll do our best to get through all the questions asked during the allotted time. And if we are not able to get through the questions because of time, our team will follow up afterwards with you directly via email or telephone to answer your questions. I'm pleased to present today's speakers from TE Connectivity on sensors for electric vehicles. First, we have Eric Brown. Eric is Director of Global E-Mobility Sensors and Transportation Sensors Product Management. Sasan Babai is our Automotive Sensors Product Manager. And Chris Couch, our Automotive Sensors Field Application Engineer. I'm going to hand it over to our presenters, and I'll come back to you at the end for questions. Over to you, Eric.
Thanks, Megan. Appreciate everyone being here, and greetings to everyone from sunny North Carolina. First, I do hope that everyone is staying safe and mentally sane in this new era we find ourselves today. In the pandemic and remote world, we do appreciate your time and your engagement. If there's anything we've all learned, it's the ability to be flexible with both our personal and professional lives. And this is probably most evident in the acceleration of the EV and the market that we find ourselves in today. Through the next 45 minutes, we'll walk through the key market trends, highlighting what the drivers we're seeing across our customer base, the key applications, how sensors do contribute towards the efficiency and the electrification of these powertrains. And then closing out, we'll go through the technology that TE is using to address these issues and the overall partner approach that we take with our customers. And then, of course, at the end, time for some Q&A. So with that, I'll hand it over to Sasan to take us through the market trends.
Thank you, Eric. Thank you again all for joining us this afternoon. So in this segment of the powertrain trends, really there are three main drivers or trends that we believe are shaping up this space that we wanted to review with you. Range extension, or also known as range anxiety, quick charge, and safety. Thanks to the continuing enhancement in all three areas, consumer adoption rate of EVs is accelerating beyond anyone's expectations, even as recently as 2 or 3 years ago. And that is in turn is resulting in faster decline in ICE market share and a slowing growth in the segment of the hybrids. So we'll cover the range extension or the range anxiety first. The average round trip to work in the US is about 32 miles. Nevertheless, despite EVs now offering well above expected daily mileage, range anxiety remains as one of the main challenges in the way of mass market adoption. Looking at the chart over to the right from energy.gov, you can see in the blue section where a typical ICE ranges anywhere from 250 to 400 miles. Now, drawing your attention to the two different lines, the green for a medium range EV vehicle versus a blue on the high side of that, you can see even dating back to 2011, where we're in the sub 100 miles range, logically speaking, that was not going to be an issue for a daily driver. Nevertheless, it was a problem then, and as we look at the progress over the last decade, which has been significant to the extent where in the blue, we are actually having EVs that compete or even surpass ICEs, the range anxiety still persists, and one that the OEMs are very focused on to really change that from a perception standpoint. So the way industry is addressing that is really a top-down, bottom-up. What I mean by that, on the supply side of the energy, much of the focus has been on the supply in the sense that the energy that is stored in the battery. Right now, lithium-ion batteries are dominating that space, and what's emerging is solid state to further enhance the energy stored in the batteries. Also, OEMs are very much focused on optimizing or maximizing the usable capacity of batteries, such as by going to more sophisticated algorithms and softwares to better monitor the state of charge of the batteries and therefore have more available energy for usage. In that space, for example, high accuracy current sensors are a huge enabler to allow the OEMs to squeeze as much energy as possible from the batteries. Now, on the other side, the bottom side of it, which is the consumption side of energy, OEMs are also increasingly focusing on improving efficiency of the electric drivetrain, whether it's reducing mechanical or electrical losses. And also, it could be also improving efficiency of other electric drive components, such as the e-motors. In that space, again, I'd like to highlight as an example, a resolver that is used, and Chris will be focusing on that as a part of the presentation, is a huge enabler to allow maximum efficiency of the electric drivetrain. Now, next, I'd like to turn your attention to the next trend, which was the quick charge, and that is closely related to the first one that we reviewed, having to do with the range anxiety. On this side, quick charge is a major aspect of industry's response to range anxiety, in the sense that as the charge time approaches the time spent typically by a consumer at the gas pump, this whole topic of EV range is going to slowly start to fade away. Looking at the table over to the right, there are 3 levels of charging that we'll review briefly. Level 1 and level 2 are more associated with what you would see at home for charging, and there are relatively low voltages, 110 and 220 volts respectively. But looking at the next 3 columns over, where we are showing the time to charge to get a range of 200 miles, the level 1, for example, will take 1.5 days, level 2, 17 hours, and like I said, these would be more suitable for an overnight type of usage. Now, going over to a level 3, there are 2 variants, a DC fast charge, or in the case of Tesla supercharging, these are the ones that are really on the forefront and pushing the envelope by utilizing a higher voltage of 480 volts. And in turn, the charge time for 200 miles range is reduced to 60 seconds and now to 21 seconds in the case of Tesla supercharging. So now we're going from an overnight charging to something that is much more acceptable to the consumer, whether it's having a meal or stopping for a short coffee break at a stopway. The chart below that shows, as of end of last year, the number of installed public locations by the levels. As you can see, level 2 is still dominating at 78,000 ports in the public locations, and the DC fast charge over to the right is at 18,000 installations. That trend right now is rapidly growing the number of ports in level 3, and to that point, that is raising technical challenges for OEMs, in the sense that the battery pack and battery management system thermal management will have to be better managed. And also the power capability of a lot of the key components in that sequence, such as the current sensors, really has to be up to a new standard to be able to handle those much higher power levels. Finally, the third trend that we talked about was safety. Here's an area where safety is on the right side in terms of helping the EVs from a consumer perception and also OEM's perspective, in the sense that The skateboard design of these EVs that are being rolled out allows the OEMs to pack the battery pack very low to the ground, which really lowers the center of gravity, and that in turn really helps the safety and maneuverability of the EV vehicles. And also, because there is a greater overlap between EVs and autonomy, and that in turn takes out the chances of operator errors, that's another area where safety could be enhanced significantly. On the other hand, there are new and unique safety challenges in EV, mainly having to do with thermal management of the battery pack, in other words, thermal runaway. We are starting to see government regulations being implemented that either directly or indirectly deal with thermal runaway. An example of that is the GBT standard rolled out by China not too long ago that is planned for implementation into 2024-25 model year timeframe. In that space, sensors again play a significant role in enabling OEMs to meet the upcoming safety standards, such as temperature sensors and current sensors that we'll be reviewing coming up next. I now hand over to my colleague Chris, who will share with you an overview of EV powertrain sensors.
Yep, thank you, Sasan. There we go. So as you said, this is an overview of EV powertrain. And here we've tried to identify several parameters or attributes that we would like to monitor in each of the subsystems of the vehicle. So starting down here with the battery sensors, of course, current is important for the current going in or out of the vehicle or out of the battery area for state of health, state of charge, and of course, temperature for individual cells and key components there is very important. But also one that might not be as well known, humidity sensor. So humidity sensor can detect moisture ingress and condensation inside the battery, and even like a coolant leak, which could lead to corrosion and possible thermal runaway event, as Sasan had mentioned. For the charge inlet, of course, temperature and current are important, especially in the case of DC fast charge, where you have high currents and high temperatures, high temperature rise. But also position sensor, like for example, a lock verification sensor that would determine if the plug during charging is fully latched, which would help prevent a safety issue known as a hot disconnect. For transmission, so EV vehicles don't typically have traditional transmissions. Most passenger vehicles have just a fixed gear ratio. But there are several position sensors that would remain in the transmission portfolio, such as a park lock, axle disconnect. Larger vehicles like buses and trucks can use a multi-speed, more traditional type transmission, which would use the output speed or like a shift position, shift gear position. For the inverter, of course, monitoring the current and the temperature of those high power electronics that are doing the switching for the motor. Thermal runaway. So this is a kind of a niche area where you create a device that can detect a thermal runaway event. This is directly tied to the new legislation that Sasan spoke of. So here we'll be monitoring temperature, pressure, and gas concentration with the goal of identifying the conditions of a thermal runaway and then notifying the occupants of the vehicle of the impending danger and giving them enough time to pull over safely and exit the vehicle. For the e-motor itself, the temperature sensor integrated into the motor stator, which I'll go to a little bit more detail, and also, of course, the position of the rotor, which I'll also cover a little bit later, how important it is for the e-motor. And then in the case of liquid cooling, whether it be a glycol solution or an oil-based coolant, temperature, pressure, the level of the reservoir are all very important. And of course, even the fluid properties. We have sensors that can measure the fluid properties of the coolant. So here we're looking at some of the TE portfolio that can cover the things on the previous slide. So what I have here is another layout of a vehicle. On the left-hand side, you can see an integrated motor generator, which is basically an e-motor that's married with the gear box, the transmission, or fixed gear ratio or reducer. And it could be for a hybrid environment or for e-motor, but they could share the lubrication, the coolant. And what you have is separate is the inverter. On the right-hand side, we have an e-axle, what we call an e-axle, and that's a self-contained propulsion unit. It has the inverter, the e-motor, and the gearbox in one assembly. So starting over here on the left-hand side, we have the motor stator temperature sensor, which is a special temperature sensor that's integrated into the motor windings. Typically, you want to integrate this in the highest temperature area to monitor the e-motor. The position sensor, in this case, we show a traditional resolver. Some position sensors that would be used in the gearbox or reducer, such as park lock in drive mode. A battery current sensor, so it's very important to monitor the current going into and out of the battery for state of charge and state of health, you know, and predicting that range, of course. And then we have over here we have a development of a thermal runaway device, which would predict that thermal runaway event, again with pressure, temperature, and gas concentration capabilities. As far as DC fast charge, we have our high current, or I guess very high current sensor. It has a double wide bus bar to handle the high currents of fast charge, upwards of 4,000 peak amps. So motor stator temperature sensor, this is a little bit different. This is a round profile, so this one can be integrated into the stator frame itself if the windings, it's not possible to integrate it with the windings. For the position sensor, we have an eddy current sensor. Because the e-axle is a very tight, very cramped space, we have a eddy current sensor that can be not just a segment, right? It's not the full donut of a rotor, of a resolver. It's only the 90-degree segment for better packaging. A position sensor in the gearbox that is a disconnect position sensor. So in terms of a secondary axle, like an e-axle that could be deactivated when you're in a two-wheel drive mode, this sensor would detect the disconnect, which it's very important to disconnect and reduce your rotating mass, right? To disconnect the wheels from the gearbox. And then on the top, we have a few other sensors, of course, current sensors, the humidity sensor that I talked about a little bit earlier, and temperature sensors for the individual battery components. So very close to every electric motor, you'll find a rotor position sensor. It's a critical EV drivetrain component. It provides the feedback of the motor position to the motor controller, and the accuracy of that motor and that drive system is directly related to the accuracy of this position sensor. So this is integrated into a harsh environment, you know, electric motors, upwards of 20,000 RPM, and we need a sensor that can constantly relay that position within fractions of a degree at that speed. So on the left-hand side, we have resolvers. So resolvers they're a passive technology. It's been around for some time. They're used widely in the automotive, aerospace, and industrial markets. What we have for the state of the art for automotive is what we call a VR resolver for variable reluctance. And this is the SCR, what we call the SCR series of resolvers. So these are platform type resolvers. They have many different sizes, many different speeds or multipliers in the portfolio. They can be built for what we call wet environments, which means that the resolver itself is exposed to gear oil, ATF splash, or even submersion. On the right-hand side, we have eddy current sensors. So these are a little bit different. They're an active technology. They use coils on a PCB and internal processing. They're slowly gaining acceptance in the automotive industry. And as I said earlier, they can be built in a smaller size, so in a segmented type construction, which gives you a smaller part, but you do pay some expense in the accuracy and the tolerance to eccentricity. Now on to current sensors. So TE has both resistive shunt and Hall technologies. We actually have hybrid sensors too that actually contain both Hall and shunt in one package. This is done to improve the functional safety for a higher ASIL level, because there's no single failure mode that would affect both technologies the same way. So in terms of technology though, the shunt has the widest range, measurement range, and the best accuracy. So we'll focus on the shunt type of the portfolio for this presentation. So on the left-hand side, we have a passive shunt. This is about as simple as it gets. So it's a precision resistor integrated into a bus bar, and it's up to the controller or battery management system to measure the potential difference of the drop across that resistor. So we've reduced the BOM, the number of parts, by eliminating the PCB. So we have a patented PCB list design. And then on the right-hand side, we have the active shunt. So this is more of a turnkey solution. This is the same shunt resistor, but it's also paired with active circuit electronics on PCB. So it includes galvanic isolation of the high and low voltages, signal conditioning, calibration. So what you receive out on the output is a calibrated output with current and temperature, and that's over a CAN interface. And now on to temperature. So there's two areas in the EV powertrain that we focus on for temperature. We have the e-motor temperature and the battery components, temperature of the battery components. So for e-motor temperature, we use a high temperature glass encapsulated NTC element with PTFE insulation, and that it's typically integrated into the motor windings or the stator frame itself, the motor stator. It has a wide working range up to 250 degrees C at the measurement head. And it's formulated and calibrated to be the most accurate at 100 degrees C. So you can see in the chart in the bottom left-hand corner, the TE part has what we call the choke point, the most accurate point at 100 degrees C, which is typically the operating temperature of the motor, versus a competitor that's calibrated most accurate at 25 degrees C. So these sensors are typically in the same area of the position sensor on the motor. So this temperature sensor could be integrated with the resolver on a single harness, and that would go to a single connector to make the installation pretty clean. On the right-hand side, We have a battery cell or battery temperature component. So these are also NTC elements, but they have a narrower temperature range than the stator temperature because, of course, batteries don't get as hot as electric motors. So the nature of batteries is that they're unique to each OEM. Some OEMs use cylinder cells, others use pouch cells or blocks. So what you need is a highly customizable solution. And of course, TE has an extensive portfolio of connectors, terminals, heat shrink, attachment methods, quite a bit of content to fit your application and customize these solutions. And then finally, we have position sensors that I talked about a little bit earlier. So there are several areas of the EV powertrain that still require position sensors, such as the park lock mechanism, the drive disconnect or axle disconnect, and even the shift position sensors. And TE has lots of experience in the harsh environment of transmission sensors. So on the left-hand side, we have our platform position sensor. This is a non-contacting Hall technology, and it senses an external magnet, and it can sense through non-ferrous materials. So for example, if you had an aluminum casting on the reducer or transmission case, and you had a moving magnet on something like a park lock on the inside of the transmission, the sensor could be mounted on the outside and sense the magnet motion through the aluminum wall. As I said, this is a platform sensor with open tooling. And what's unique about it, though, is it's highly customizable for the application. So we will custom program this part for the specific travel, the magnet air gap, the type of movement for the application, the type of movement being linear, on-axis rotary, or arc segment type motion. It's a standard output of PWM, and of course, analog or cent is also possible. On the right-hand side, we have an angular position sensor. It's a non-contacting Hall as well, but the target magnet is internal. So the customer's shaft would interface with the rotor of the sensor and rotate it on axis like an end of shaft type application, and the magnet would be mounted to the rotor and move internally. This is also a platform design and is a digital cent output. And now I'd like to hand it over to Eric, who can tell us about the TE advantage.
Yeah, appreciate it, Chris. And thanks for taking the time to walk through a couple of those key technologies. Again, the overall point that we bring here is really from a TE standpoint, terminals and connectors and sensors. Our job is really to make our customers' systems smarter, more efficient, and better suited for the end customer. So I'll just highlight a couple of these key areas on the top. Most of everybody on the call knows TE as a terminal and connector, and not only terminal and connector, but a global leader in contactors and wiring for EV. This internal expertise really gives us the ability to leverage that towards our sensor business. We've lived the development cycles, we know what the strict requirements are, and we have the labs also internally to apply our sensors to these types of vehicles. From a market and application standpoint, our strength is really in the products and technologies that we've launched into the market and the partnerships we have with our customers to find solutions for their systems. As Chris mentioned, there's a lot of customization in this space. Every customer wants their system their way, making their competitive advantage. This really ties into not only our ability to customize through our molding and stamping capabilities, but also internally owning our IP. Just as an example for the market that we have, for the resolvers, which are key in the electric motors, TE already has produced over 2 million of these resolvers that are actively installed in our customers' electric vehicles globally. So really building on that application know-how is helping us move forward. Lastly, I will touch on global manufacturing footprint, and this also extends to our local support. So TE's philosophy is we want to be where our customers are, meaning we want to produce in the region our customers are consuming. We also want to be able to support our technical teams in the same region. The TE footprint really allows us to be flexible on where we're putting manufacturing, since we own facilities in every region. For us to expand to NAFTA or to China, for example, we don't have to worry about constructing a new building, qualifying the facility, on and on. We leverage our existing manufacturing facilities that already have ISO TS compliance and use their automotive expertise when we are installing new technologies and new lines. I think overall, the point that I'd like everyone to walk away from is really TE is offering our customers an end-to-end solution in the EV space, from terminals and connectors through sensors, really supporting that system need. So with that, I will open it up for Megan, if you want to return back to you, and a couple of questions that we might have coming in.
Super, thanks, Eric, and thanks Sasan and Chris for that. So let's start with some questions here. The first one I'm going to send over to Chris, and the question is, what is the system value of using passive versus active current sensors within the battery management system?
Thank you for that question. It really depends on the customer's battery management strategy. So, for example, if they already have a battery monitoring module that is sampling cell voltages and is already dealing with analog signals that are on the high voltage side, and already has that built-in galvanic isolation and in-system calibration ability, then a passive shunt would probably be the best solution for the most economic approach. On the other hand, if the customer is looking for more of a, like I said, a turnkey solution where they have a CAN bus or a CENT bus already, but they don't really have that battery management module in their system, they can go for an active current sensor, which is already calibrated and will interface with the CAN. You don't have to worry about galvanic isolation or any other complications with dealing with high voltage.
Super, thanks, Chris. The next question I have, I'm going to ask for Sasan. The question is, what other trends have you seen regarding the OEMs and electrification of the powertrain?
Thanks, Megan. That's a great question. Really, I can perhaps think of two other ones that we didn't cover in today's presentation. The first of which I would say having to do with OEMs as they enter sometimes second, third, or even fourth generation platforms of electrified vehicles. They're increasingly focusing on further integration and optimization of their electric drivetrains. And what that means for a lot of the component and subsystem suppliers is oftentimes more stringent requirements, because there is going to be less space for packaging as they further integrate the system solutions. And also at times, there are other engineering challenges such as thermal management as the components get closer to one another, thermal management, the thermal mass, all of those things move in the direction of a more challenging problem for the engineers. The other one that I can think of is increasingly focusing on optimizing and doing the trade-off between energy and power density. What I mean by that, the energy density really correlates with more range, but the power density is more peak power demand. And as OEMs are entering those second, third generation vehicles, they are having to try to have systems that can really meet both ends. And a lot of times those are in conflicting directions. And the goal is to try to commonize as much as possible. So you have maximum range possible, but then you're also able to serve a very small fraction of end users that may want to take their vehicles to the track and really run it at a very peak performance area. So to do the system or subsystem designs that can really handle both ends brings a new set of challenges, and one where TE is enabling a lot of the OEMs in that space.
Super, thank you, Sasan. The next question that we have here, I'm going to send back over to Chris. What is the driving factor to utilize eddy current versus resolver?
Yeah, again, it's more of a customer preference, I think. So eddy current is a newer technology, but it is designed as a drop-in replacement for a resolver. So if you were to look at the controller that's seeing the signals, it's not going to be able to tell the difference as far as a functionality standpoint. So resolvers have the longer track record. That's the state of the art in automotive right now. And they are, at least at this point, more robust in terms of the wet environment. So if it's exposed to oil splash or submersion, the resolver would be what we would recommend. On the eddy current side, you can design it into a smaller package. So for the e-axle application I talked about, you have some advantages there, in saving space if you can go with an eddy current type sensor. Also, as far as the BOM cost, the eddy current sensor uses less metal, less stamping, those kind of components. So it's actually in terms of the BOM, it's a little bit of a cost savings.
Okay, super. Thank you for that, Chris. The next question I'm going to send over to Eric. And the question is, what steps are your customers, component manufacturers or OEMs, taking to prevent battery thermal runaway?
I think at thermal runaway, it really becomes a system level strategy and a system level discussion. The two leading focus areas that we're finding our customers looking at is really kind of this 5-minute how to detect a thermal event once it's already occurred. And that 5-minute kind of system view gives a passenger enough time to actually stop the car, exit the car, and be safe, right? The other approach is a indicator of early warning. I think Sasan hit on this. It's a little bit towards the 20-minute. And this is a combination of a few sensors. Specifically, the current sensor within the system needs to be very, very accurate in order to detect early voltage issues and start to give that lead time of raising the hand and saying, hey, there might actually be something wrong here, sending a maintenance signal, stopping the car, things like that. So it really depends on which area our customer is focused on, whether it's early detection, state of health, predictive maintenance, or if they're trying to take something's already occurred, we just need it for a safety. And again, that's a combination of a number of sensors, temperature, pressure, gas potentially.
All right, great. Thank you, Eric. I've got one more question here, and so I just want to encourage everyone that's still on the line with us, if there are questions that you have, please feel free to submit those into the chat box now. But the question here that we have last is for Sasan, and what is your expectation in terms of future functional safety requirements as it pertains to sensors in electric vehicle powertrains?
Thank you, Megan. As Eric touched on this, there is increasingly focus by governments and OEMs on further enhancing the functional safety of EVs, more specifically thermal runaway. And on that front, it is a mixed bag in terms of how every OEM is challenging the same goal, in the sense that if you look at it as at a subcomponent level, let's take a current sensor as an example. There are extremes where OEMs may be targeting the trend where it's pointing towards an ASIL C or an ASIL D functional safety standard, but they may be able to get to that same endpoint many different ways. So this is where it's a case by case, depending on what the OEM functional safety strategy is overall, and how does that trickle down to all the building blocks, the current sensor being one of them. So what I mean by that, on one extreme, there could be a case where in the case of sensors, any given OEM may decide to have that component to be an ASIL C or ASIL D compliant, or they may be able to build in a system level architecture that has the redundancies that will give them that ASIL C or D, and they can possibly get away with a lower ASIL standard components. Again, it's a mixed bag, but generally speaking, the trend is towards a much higher functional safety requirements to meet the consumer expectations.
Super, thank you so much, Sasan. And with that, I think we don't have any further questions. So I want to thank everyone for taking the time to join us today. You will receive an email following up after this with a recording of the webinar. And if you have any questions for our team, feel free to contact us directly. We appreciate everyone joining in your time. Have a great rest of your day.